All right, so let's learn what a matrix norm is. Specifically, we're going to be looking at matrix norms that are induced by a vector norm. What that means is that there's lots of ways we could define a matrix norm. So here, A represents some matrix, and so we're trying to come up with some way of describing a norm for this matrix. Or in other words, a way of measuring how big the matrix is. What's the size of this matrix? Just like the norm of a vector describes to us, in some sense, how big the vector is. Now, there's lots of ways we could define a norm of a matrix. As long as we come up with some rule that satisfies those same three criteria that we talked about with vectors, if I take the norm of, if I follow this norm rule for a matrix, I should always get something greater than or equal to 0, and I should only get 0 if I'm taking the norm of the 0 vector. And all those other criteria that we talked about with vector norms, as long as you come up with any rule that satisfies that criteria, then great, you've got a norm for a matrix. You've come up with some way of finding the norm of a matrix. What we're doing here, though, is specifically looking at the norm of a matrix that's induced by what we already know about vector norms. Okay, so in other words, we're defining our matrix norm in terms of norms of vectors. So notice over here, so this little triple equal sign here is basically saying that this is how we're defining our matrix norm. So our matrix norm, we're going to define it to be the max of the norm of these vectors. Notice if A is a matrix and V is a vector, and this product A times V is defined, then A times V is a vector. So over here on the right hand side, these aren't matrix norms, these are vector norms, things that we already know, things that we've already studied. So what this is saying is, take the collection of every single vector that exists that has norm 1 and do A times all of those, and whichever one of those gives you the biggest vector, that'll be your norm for your matrix A. The problem, I guess you can probably imagine the problem with this definition is there's infinitely many vectors that satisfy this condition here that have norm 1. For example, in R2, if you just think of the unit circle, the unit circle is a set of infinitely many points that satisfy that condition. Alright, so how in the world are we going to do this if there's infinitely many vectors that satisfy that condition? I can't find the max over all of those if there's infinitely many of them for me to check. And this other way of defining our matrix norm, and we're not going to prove that these two things mean the same thing, you can just take my word for it. It really doesn't get any better. We're saying here, let's look at every single vector that's not the 0 vector. That's our condition that we're looking at here. And let's do A times any vector that's not the 0 vector, divided by, and take the norm of that, and then divide by the norm of that vector. And that's the biggest one of all of those, the max of all of those, is our matrix norm. And again, that seems impossible because there's so many vectors, pretty much every vector except for one, that satisfies our condition of not being 0. So how in the world could we ever possibly measure this? Fortunately, in your book, theorems 741, 742, and 743 give us nice shortcuts on finding this matrix norm under certain conditions. So they tell us, all of this kind of depends on which type of vector norm we decide to do. So if we decide to say, all right, I'm going to define my matrix norm in terms of the 1 norm for vectors, then we already know how to do the one norm for a vector, and the theorem 741 gives us a nice shortcut for calculating our matrix norm in this case. All right, so our matrix norm that's induced by the one norm for vectors, our one norm for a matrix, is equal to the max of all of our absolute column sums. So what does that mean? That means if I have the matrix -1, 3, 5, 2 is my matrix A, then the max of my absolute column sums, let's just take each column, take the absolute value of each entry and add them up. So do absolute value -1 plus absolute value 5, that's 6, and then do absolute value 3 plus absolute value 2, that's 5. So the one norm for this matrix, the norm that's induced by the one norm for vectors, is 6, the max of these two sums. Okay, so it's really interesting that this thing that seems impossible, this idea of taking the norm over infinitely many vectors and picking out the biggest one, that seems impossible, but they go through the proof, and I encourage you to read that proof so you can see if you can follow along with what they're saying in that proof. They prove that we have this really nice shortcut if we're dealing with the one norm for vectors. Similarly, if we're doing the let's see, the infinity norm for vectors, then it turns out that this thing that seems impossible up here, if we define this in terms of infinity norms for vectors, then our infinity norm for a matrix has a nice shortcut as well. It's just the maximum absolute row sum. So instead of adding up across the columns and picking the biggest number, add up across the rows and pick the biggest number. All right, so this is, we take the max absolute row sum. Key word here is absolute. We're not just taking the numbers like what we did a second ago. It's not just the numbers that we're adding up, it's the absolute value of the numbers. All right, so if I take this same matrix and want to know the infinity norm for this matrix, the norm induced by the infinity norm for vectors, then I just add up across my rows. So I do absolute value -1 plus absolute value 3 is 4, and then absolute value 5 plus absolute value 2 is 7. The max of those row sums is your infinity norm. So in this case, the norm of this matrix A, if we're using this infinity norm, we would say is 7. All right, and then we have one more common norm that we use with vectors. That's the 2 norm. So again, the same idea. I can define my matrix norm in terms of 2 norms of vectors. So if I turn these vector norms into 2 norms and use what I know about the 2 norm for vectors, we have a nice shortcut that shows up for this as well. This one, they don't really give you the proof in the book because it's kind of beyond what we can talk about in this class. They refer to some other theorems that you would need that we're not going to be covering. But the norm induced by the 2 norm for vectors, what you do there is you take the square root of the largest eigenvalue of A transpose A. All right, so that sounds strange. So do the square root of the largest eigenvalue of the matrix A transpose times A. All right, so again, that sounds really strange. Where in the world did that come from? It's kind of sad that they can't give you the proof of that, where that comes from. But this is just going to be one of those things that you have to, I guess, take our word for it. I will mention, for those of you planning to go to grad school, the two proofs that they did give, they did prove to you why the 1 norm is what it is. They proved to you why the infinity norm is what it is. For those of you going to grad school, it's pretty likely that at some point along the way you're going to have to memorize those proofs. So may as well go ahead and get a head start now if you want to. But the largest eigenvalue of A transpose A, take the square root of that, and that gives you your 2 norm for the matrix A. Since I just made up this matrix here, I don't know the eigenvalues for it. I'd have to do a little bit of work. I don't really want to do that work right now. And actually I'd have to do A transpose times A first and then find the eigenvalues of that. So I'll skip that. You can look at example 742 in the book if you want to see an example of finding the 2 norm. But the main idea I want you guys to get out of this video is, it sounds, I know when you're reading it, it sounds weird. What do they mean by matrix norm induced by vector norm? What are they talking about? But the basic idea is that if we define a matrix norm in this way, or in this way, they mean the same thing, then you can check, and this way of defining a matrix norm is valid because it satisfies the 3 criteria for a norm. Okay, if you follow this rule, you're guaranteed to always get something greater than or equal to 0 for your answer. And you'll get 0 for your answer if and only if A is the 0 matrix. If you do the norm of some number times A, it'll come out to be the same thing as the absolute value of that number times the norm of A. And this satisfies the triangle inequality. So if you define a matrix norm in terms of one of these 2 rules here, it's a valid definition for a norm because it satisfies the criteria for a norm. And then the other thing that you need to get out of this lesson is that how this all works out depends on which vector norm you use. And in our 3 main vector norms that we talked about in the previous video, it turns out that we have some nice shortcuts for finding the norms induced by those 3 different vector norms. All right, so I don't know, hopefully that helps you understand what's going on with these matrix norms, and that should also help you understand a few things that you'll be seeing in your homework.